Hello students, welcome to MEMONEET. This is Ravikant, your physics teacher, and today we are going to discuss about the topic refraction through the curved surfaces. We in the last two parts saw reflection through the curved spherical mirrors, and then we saw refraction through the plane surface and prism. Now in the third part of this ray optics, we will see the refraction of the light ray through curved surfaces. Right, in the last part we saw refraction through plane surface. Now we'll see from the curved surface or the spherical surface, and then we will be going forward to the lenses, and then finally we'll study about the optical instruments. Right. So let's see how the refraction is taking place on a curved surface. There are two types of curved surface. We can say there is one is a convex and the other one is a concave surface. Now suppose this is a sphere. Let me do it like this, right? Now this is a curved surface, and if I draw the boundaries for it, this would be boundary, right? Uh, right. Now similarly the other boundary. Now this is the curved surface. Then if the light ray is traveling from this side, right, then this is a convex surface, right? This is a convex surface. Now what we will be studying, or what we will be how we will be studying this is that this part is one medium and this part is the another medium. The medium, or the you can say the interface, is of curved shape, and here the interface is of convex shape. The medium containing incident ray or the incident angle, as always, will be medium, will written as mu1, and the medium containing the refracted angle will be written as mu2, right? While studying this refraction through curved surfaces, we have to understand, we have to take three main assumptions. The very first assumption is the objects which we will be using over here will be point object, right? They will be point objects. Second assumption is that the angle made, the incidence angle and the refracted angle will be very small. And the third assumption is here the aperture of the curved surface will be very small. Uh, Having these assumptions in our mind, we will be drawing the ray diagrams. So if suppose this is a line passing through the optical center, this is a line passing through the optical center of the curved surface, or you can say the geometrical center of the curved surface, right? Suppose this is a line. Okay, now here is the point object O. So let one ray pass through this line, and because it is normally incident, it will pass undeviated. Somewhere here will be the center of curvature of the curved surface, right? Now we'll take another light ray which is traveling at an angle, traveling at an angle, right? It is incident at this point. This is the incident ray. So if we draw a line like this, so this line will be acting as normal. Then since the light ray is traveling from mu1 to mu2, and what we are considering here is mu1, is less than mu2. That is, the refractive index for the first medium is less than the refractive index of the second medium. That is, the light ray is moving from a rarer medium to denser medium. Therefore, the light ray will, after refraction, will bend towards the normal. So we can say that the refracted ray travels like this. It travels towards the normal, and the ray travels somewhat like this, and this is the point where we are getting the image, right? This is the point where we are getting the image. This is normal, this is incident ray. So let this be angle of incidence I, and this will be the angle of refraction R. Let this be angle alpha, right? Let this be angle beta, and this be angle gamma, right? So now by using these angle and doing lot of geometry, because we are not going to discuss about the derivation of this, but finally doing all the derivation, what we get as a formula is that, before telling the formula, if this is the optical center, this point, this length will be your object distance, and this will be your image distance, right? So the formula for the relation between VU and mu1 and mu2 is that mu2 upon V minus mu1 upon U is equals to mu2 minus mu1 upon R. Mu2 minus mu1 upon R. Now, let's talk about this formula. This formula is relating your image distance, object distance, refractive index of the two mediums separated by the curved surface, and the radius of curvature of the curved surface. What is the radius of curvature? Radius of curvature is the distance between this point and the center of curvature. So this will be your radius of curvature R, right? This is radius of curvature R. Now what we are supposed to remember over here is that this formula, the very first thing is that this formula which I have written over here is valid for both concave surface or convex surface, right? Very first thing is this. The second thing is that in this formula, mu1 will always be the medium containing the angle of incidence, and mu2 will always be the uh, medium, refractive index of the medium containing angle of refraction, right? What I am telling is that in this formula, mu1 will always be equal to the refractive index of the medium containing incidence angle, and mu2 will always be equal to the refractive index of the medium containing refracted angle, right? So what two things I told you till now is, the very first thing is that this formula is valid for whether it is a curved interface, or a convex interface or a concave interface. Second thing is, as I told you in the beginning, also not in the beginning of the ray optics, in the first part of the second part, in the second part, I told you that mu1 will always be the medium, be the refractive index of the medium which contains angle of incidence, and mu2 will be the refractive index of the medium which contains refracted angle, right? Then your radius of curvature, while you will be putting the value of radius of curvature, you will be following the sign convention. Sign convention will be the same as I told you in the case of the mirror. What? Where all the distances which are to be measured will be measured from the optical center of the curved surface. What is optical center? That is the geometrical center of the curved surface. This point. This point will be the point from where the measurements are to be taken, right? Now when measurements are to be taken, and while taking the measurement of the distance, if you are moving in the direction of incident ray, then the distance measured will be taken as positive, and if you are moving in the direction opposite the incident ray, then the distance taken will be negative. For example, here if we calculate the radius of curvature, to measure the radius of curvature, we will have to move from this point to this point, right? Here is the center of curvature. So we are moving in the direction of the incident ray, because incident ray is moving from left to right. So while measuring the radius of curvature, we are also moving from left to right. Therefore, here For this case, the radius of curvature will be taken as positive. Similarly, the image distance will be taken as positive, but the object distance will be taken as negative, right? So the first thing is that this formula written over here, mu2 upon v minus mu1 upon u is equals to mu2 minus mu1 upon r, is valid for both convex and concave surface. Second thing is that mu1 is always the refractive index of the medium, containing incident angle. Mu2 is always be the refractive index of the medium containing refracted angle, right? Second thing is value of u, v and r will be put, we have to put with sign convention. Sign convention is that whenever we are measuring any distance and we are moving in the direction of incident ray, the distance will be taken as positive, and if you are moving in the direction opposite the incident ray, the distance will be taken as negative, right? So using sign convention we can do this, right? So whenever you are writing the values, you are putting the values in this formula, always remember mu1. In mu1 you will be putting the value of the medium which contains angle of incidence, irrespective of it being a denser medium or it being a rarer medium. See, in this diagram what we have shown over here is that the light ray is traveling from a rarer medium to a denser medium. If the light ray is traveling from a denser medium to a rarer medium, then too the denser medium is containing angle of incidence. So if denser medium is containing angle of incidence, we will put the refractive index of denser medium in mu1 only, right? In mu1 only, right? So this formula is important. This formula will give you the relation between u, v, r, mu1 and mu2. Okay, now for this, just to make you understand what I'm trying to make you all understand is, let me solve a numerical for you. Yes. Now just to understand it, see what the question says is that there is a sphere, glass sphere, right? And this is the diameter of the glass sphere. This is the center, and it says that a small air bubble in a glass sphere of radius 2 cm appears to be 1 cm from the surface when looked at along the diameter, right? If the refractive index of the glass is 1.5, find the true position of the air bubble. So this air bubble, there is air bubble somewhere here, right? And it appears to be at 1 centimeter. So they have given that image distance is as 1 centimeter, right? Now this radius is given as 2 centimeter. This radius is given as 2 centimeter. This is a glass sphere, so its refractive index mu2 is equals to, oh sorry, let me write it, mu g is equals to 1.5, and this is air, that is mu will be equals to 1, right? Mu will be equals to 1. Now we have this image distance with us, we have mu1, mu2, and we also have r. Now if this is the object, the light ray will be traveling like this, right? Light ray will be traveling like this, and after refracted it will be traveling in this way. It means the light ray is moving from a denser medium to a rarer medium. What formula do we have? We have a formula as mu2 upon v minus mu1 upon u is equals to mu2 minus mu1 upon r, right? So mu2 is the medium in which there is a refracted angle or the refracted ray, and mu1 is the medium which contains incident ray. So according to this concept, mu1 will be equals to 1.5 and mu2 will be equals to 1, right? Next, if we write u is unknown to us, and if we find v we can see it is from this point, that is the point optical center, it is 1 centimeter in the opposite direction. So v will be taken as minus 1 centimeter, right? V will be taken as minus 1 centimeter. Then if we talk about the radius of curvature, again the radius of curvature is to be measured from this point. So radius of curvature is also being measured in the direction opposite of the incident ray. So radius of curvature R will be taken as minus 2 centimeter, right? So now let's put the value. So putting the value, we get 1 upon V is minus 1. 1 upon minus 1 minus 1.5 upon u is unknown to us is equals to your mu2 minus mu1. mu2 minus mu1 matlab 1 minus 1.5 upon minus 2, right? So from here we'll get minus 1 minus 1 minus 1.5 upon u is equals to minus 0.5 upon minus 2, right? So this will make this minus and minus becomes plus, 5 ones are 5 fours are. So what we are finally left with is minus 1.5 upon u is equals to 1 upon 4 plus 1. This implies that minus 1.5 upon u is equals to 5 by 4, right? 5 by 4. So 5 ones are 5, 0.3s are. So from here we get u is equals to minus 1.2 centimeter, right? So the correct answer for this is minus 1.2 centimeter. That is the correct position of the air bubble is 1.2 centimeters from the curved surface, right? 1.2 centimeter from the curved surface, but when we are viewing it from outside along the diameter, it appears to be at 1 centimeter, right? So this is how you are supposed to do. I'm repeating the things again, not for the numerical, for the numeric, is for the formula which we have seen. So that is, this formula is to be used when there are numericals related to the related to the refraction through the curved surface. Now, irrespective of the surface being a concave or a convex, see, if it is a concave and a convex, what will differ is the radius of curvature, right? Either the radius of curvature will be positive or it will be negative, right? How radius of curvature will be positive or negative? If it is a concave or a convex, depending upon the light ray either traveling from a denser medium to a rarer medium, you can easily find the direction, the sign of radius of curvature, right? So the formula is mu2 upon v minus mu1 upon u is equals to mu2 minus mu1 upon r, right? This is the formula. What you have to remember in this is, this formula is valid for curved for both convex surface and as well as for a concave surface. Second thing is, mu1 is always the medium containing the incident ray, whether it is a denser medium or a rarer medium, no issues. Put the refractive index value over there. And mu2 is always the refractive index of the medium containing refracted ray, right? V and U are to be put with their sign convention. R is also to be put using sign convention. What is sign convention? All the distances are to be measured from the curved surface to the point, and if while doing so, if while measuring, we are moving in the direction of the incident ray, the distance measured will be taken as positive, and if we are moving in the direction opposite the incident ray, the distance is to be taken as negative, right? So this is about refraction through the curved surface, right? Refraction through curved surface. Now, when we combine two curved surfaces, we get a lens, right? So suppose these are two surfaces combined together. So this will give you a convex lens, right? So if this is the first curved surface, then this would be R1, and if this is the second surface, this would be your R2. Now coming to a concave mirror, this is one of the curved surface, this is the another curved surface, right? We join it like this. This is a concave lens, concave lens, right? And for this R1 will be in this direction and R2 will be in this direction. Now what thing which you have noticed, which you have to remember here is, or notice here is, that is the convention that we are always taking the left curved surface as the first surface, and therefore we are taking radius of this surface as R1, whether it is a concave lens or convex lens, right? The radius of the leftmost surface, this will be taken as R1. For this leftmost surface is this, so its radius is R1 here, right? Its radius is R1. Okay, so when we combine two curved surfaces, they form a lens. So for convex lens, this type of lens is known as biconvex lens. Both the sides are convex. There is another type of lens which is known as plano-convex. So the first side is plane, the another side is convex. First side is plane, the second surface is convex. So this is known as plano-convex. This is plano-convex. Second is third is your convex. Uh, Third is your concavo-convex, right? Yeah, it's concavo-convex. So concavo-convex, concavo-convex, concavo-convex. This is your concavo-convex, right? Similarly, in concave mirror, this is plano-concave, this is plano-concave, and then convexo-concave, right? This is convexo-concave. So if you see the difference, for a concavo-convex, the edges are pointed, sharp, but for convexo-concave, the points are blunt over here. They are not narrow as it is in concavo-convex. So this is the difference. So these are the type of the lenses you may come across, right? Now let's coming to the nature of these lenses. If we talk about convex lens, so light rays traveling from infinity will always converge at a point, right? They will always converge at a point, and this point will be known as focus. Therefore this convex lens is considered as a converging lens. Now the equivalent diagram for this lens is a prism, then a glass slab, and then a prism, right? Now we have seen in the refraction through prism that any light ray traveling in the prism after reflection bends towards the base, right? Similarly, from this prism also the light ray after refraction will bend towards the base, and a light ray normally incident on the glass slab will travel undeviated, right? Undeviated. So from here what we find is that this convex lens, from this diagram it gets clear that how convex lens is a converging lens. Now if we talk about a concave lens, if we talk about concave lens, right? So the light ray coming from infinity which are parallel to each other will travel as if they are coming from a point, and this point is known as focus, right? So what we find here is that the two light rays are getting diverged after refraction. So this concave lens is known as diverging lens, To understand its diverging nature, we can draw it like this, that it is a inverted prism over a glass slab and again an inverted prism, right? So the light ray traveling through the prism will refract towards the base. Light ray incident normally on the glass slab will refract undeviated. Then again a light ray getting incident on the prism will refract bending towards the base, right? And this is your concave lens. This is your concave lens, right? So what we find is that convex lens is converging, right? Whereas concave lens is diverging in diverging in nature, right? So convex lens is converging and concave lens is diverging in nature. Next, now moving forward, next thing is terms related to lens. So if this is a convex lens, its geometrical center is known as your optical center, right? Optical center for a concave lens, right? Then this first curved surface will have its center of curvature over here. We'll write it as C1. Second curved surface will have its center of curvature here as C2. Then the line passing through the center of curvature in the optical center will be known as principal axis. Similarly, for a concave lens, here we will have C1 and here we will have C2, right? So a line passing through C1 and C2 and the optical center will be known as principal axis. Now this surface, this region is known as the aperture of the lens. This is known as the aperture of the lens. Similarly here, this region is known as the aperture of the lens, right? Now as we saw here in this diagram, that the light ray traveling parallel to each other or parallel to the principal axis, they converge at a point, or they appear to converge at a point, and that point is known as principal focus. So for a convex lens, if this is a convex lens, this is the principal axis, this is not the principal axis, and if this is the principal axis and this is a light ray parallel to the principal axis, this is another light ray traveling parallel to the principal axis, they after refraction pass through a point, and this point is known as your focus, right? And this is your optical center. So the distance between the focus and the optical center is known as focal length. Distance between the optical center and focus is known as focal length. Similarly, if you go for a concave lens, this is your concave lens, this is your concave lens, this is optical center, this is principal axis, light ray traveling parallel to the principal axis, it will travel as if it is coming from a point. A light ray traveling parallel to the principal axis after refraction will travel as if it is coming from a point, and this point will be known as focus, and the distance between the focus and the optical center will be known as focal length, right? So we have seen your principal focus and focal length as well, right? Focal length as well. Now using this we will be drawing the ray diagrams. Using this we will be drawing the ray diagrams. Let me check first. So again, as we saw in the mirror, here also we have some rules, or we have some rays which we are supposed to use to draw the ray diagram. So the first ray which we are going to use is that is parallel to principal axis. Principal axis. So any light ray traveling parallel to principal axis will always travel or always pass through the focus. So this is the principal axis, and the light ray is parallel to the principal axis. It will pass through the focus. It will always pass through the focus. This is the optical center, right? Similarly, for a concave lens, this is the optical center. This is the principal axis, and the light ray traveling parallel to the principal axis will refract as if it was coming from the focus, right? It was coming from the focus. Now, the second light ray which we are supposed to use is second second light ray which we are supposed to use is that a light ray passing through focus, right? A light ray passing through focus. So if this is your convex lens and this is this is the principal axis, and if this is the focus, then the light ray passing through the focus after refraction will travel parallel to the principal axis. Similarly, for a concave lens, if this is the principal axis, this is the optical center, and if this is the focus. So a light ray is incident as if it was coming from focus. After refraction, will travel parallel to the principal axis, right? Then the third type of ray which we can use for the image formation is third type of ray which we can use for the image formation is the ray passing through optical center. Optical passing through optical center. So as we know that this optical center is the geometrical center of the aperture of the lens, therefore any light ray passing through the optical center will always go undeviated, whether it is a concave lens or a convex lens. This is optical center, this is principal axis. Light ray passing through the optical center will go undeviated, right? It will go undeviated. So these are the three rays which we are going to use for the image formation using this convex lens and concave lens. So let's finish up the image formations first, then we will look into the lens maker's formula, which is the most important thing for this, right? So lens maker's formula, then we'll get the lens formula and then magnification, right? So the first image formation is using a convex lens, and it is for the case when the object is at infinity. So when object is at infinity, and if this is your convex lens, this is the principal axis, this is the convex lens, right? Let me do it again, right? See, object is at infinity. Now object is at infinity and we are taking a convex lens. This is a convex lens, right? Now we take a line to draw the principal axis, right? Let this be the principal axis, right? Then light ray is coming from infinity, so it will, the rays will be parallel to each other. So the rays will be parallel to each other. This is the first ray. This is the first ray, and second ray. Now both are incident. Now after refraction, these rays will pass through a point which is known as focus, right? So this is one of the ray. This is the another ray. So this is your optical center, right? This point will be the focus. So light coming, if the object is placed at infinity, then the light coming from the object will be traveling parallel to each other and will be parallel to the principal axis. And when the light rays are parallel to the principal axis, they intersect at a point or they pass through a common point which is known as the focus. So the image will be formed at focus, right? Now the second case is when the second case is when the object is placed beyond 2f. What is 2f? It is a distance from the optical center which is twice the distance of focal, twice equal to the twice the focal length, right? So the second case is when the object is, second is when object is is beyond beyond 2f, right? So let me draw again. This is a convex lens and this is a convex lens. This is the principal axis, right? Now if this is the principal axis, let me draw this as optical center. If this is f, this will be f, this is 2f, twice the distance of focal length, and this will be your 2f, that is twice the distance of focal length. Then this is the object, right? This is the object. So let's draw the incident ray now. This is the incident ray, right? Now this is the incident ray which is, let's say, is parallel to the principal axis. So since it is parallel to the principal axis, after refraction it will pass to the focus. So it is passing through the focus, right? So now the next ray we can take is that a ray passing to the focus. So a ray passing to the focus will be like this, yes, and then after refraction this will travel parallel to the principal axis. So it travels parallel to the principal axis, right? So this is the point of intersection of these two refracted rays. So here will be the image formed. So if we get the image here, this is the image, this is the image formed, right? Now if this is the image formed, if we write the characteristics over here, the image formed is by the actually refracted light rays, therefore the image formed is a real image, right? What else? It is inverted. What else? It is between f and 2f on the other side, right? F and 2f on the other side. Now if we talk about the object distance and image distance, this is the object distance, this is the object distance u, and this is the image distance v, which we can easily see that here u is greater than v. It means the image is of smaller size, so we can write that image form is diminished, right? The image formed is diminished. Now next case, when the object is at 2f, right? Object is at 2f. So if this is the convex lens and this is the principal axis, right? Let this be the optical center, this be the focus, let this be 2f. Similarly on the other side, this be the focus, and let this be 2f, and the object is placed on the 2f position. Now incident ray parallel to the principal axis. After refraction will pass through the focus. After refraction will pass through the focus. Then the second light ray, let it pass to the focus. So after refraction it will travel parallel to principal axis. Right. So this is the point where they are intersecting. This is intersecting. Therefore the image will be formed at this point. So the image is formed at 2f. The image is formed at 2f. This is the image where it is in form. So if I write the characteristics from here is, then it is real image. Next it is inverted. What else? It is at 2f, and because both the sides the position is of 2f, therefore it is of same size. Same size. Why? Because u is equals to v. Right? Here u is equals to v, therefore it is of same size. Now next is your case when the object is between 2f and f. Fourth is when object is between f and 2f. So this is the convex lens and this is the principal axis. right? So let me mark this as optical center. Let this be F. Let this be 2F. On the other side also we can mark it as F and 2F, right? Now the object is being placed between F and 2F, right? So if this is the object, this is the incident ray. So since it is parallel to the principal axis, after refraction it will pass through the focus. So light ray will pass through the focus. Okay. So this is the refracted ray. Then the second light ray will again pass through the focus and will after refraction travel parallel to the principal axis. So if this is the case, the light ray passing through the focus after refraction will travel parallel to the principal axis. Right. So they intersect at this point. They intersect at this point. So the image formed is beyond 2F. Image formed is beyond 2F. So if we write the characteristics, what are the characteristics? Characteristics are real, then it is inverted. What else? It is beyond 2F and it is enlarged. Why it is enlarged? Because here we find that V is greater than U. Why V is greater than U? Because U is this distance, that is between 2F and F, and the image distance is beyond 2F, right? So image distance is greater than object distance, therefore the image form will be enlarged. Then fifth case is the case when the object is placed at focus, right? So fifth is your when object is at F. When object is at F, if this is the convex lens, this is the principal axis, right? This is optical center. Let this be F, this be 2F, similarly this be F and this be 2F, right? And the object is at focus. Then the light ray, first light ray is traveling parallel to the principal axis. After refraction, it passes through the focus, right? This is incident ray, this is refracted ray. Then next light ray we will take that which is passing through the optical center. It travels undeviated. So what we find is that the light ray after refraction they travel parallel to each other and therefore they will meet at infinity. So the image will be formed at infinity, right? So when the object is placed at focus, the image is formed at infinity. Now the sixth case is the case Sixth case is the case when your is between object is between F and O, that is, it is between optical center and focus. Now, if this is your convex lens, this is the principal axis, right? Now, this is the optical center. Let this be F, and the object is between O and F, right? F at this side. So, a light ray traveling parallel to the principal axis always travel through focus after refraction, right? So, this is the first light ray parallel to principal axis after refraction passes through the focus, right? The second light ray will again take it from optical center. So, light from the object passes through the optical center. Yes. So, if this is the case, what we find that these two light rays are what getting diverged. So, we can say that when these light rays are produced backward, when these light rays are produced backward, they appear to meet at a point. They appear to meet at a point, and the point where they meet is the point where the image has been formed. So this is the point where the image will be formed, right? So from here, what we see is the image over formed here is virtual and erect, virtual, erect, at same side, and is enlarged, right? It is enlarged, and this is the case when a convex lens is used as a magnifying glass, right? So when a convex lens is used as a magnifying glass, this is the ray diagram which represents how we get a magnified image or enlarged image of a given object when we use a convex lens to magnify it. So when we are using a convex lens as a magnifying glass, the object of which we need the image is placed between the focus and the optical center of the convex lens, right? Then this is all for this image formation using convex lens. Now coming to your image formation using concave lens. So it has only one ray diagram. So let me draw it like this. If this is your concave lens and let this be the principal axis, right? And this be the optical center. Let this be F, be 2F. Similarly, this be F, and this be 2F, and we are randomly placing a object at some point. Now a light ray, first light ray we are taking parallel to the principal axis, right? First light ray we take parallel to the principal axis, and after refraction the light ray will pass through the focus, right? This would be the case. This is a refracted ray and this is the incident ray. Then sorry, yes, this would go like this, no? Will get refracted like this, right? Now a light ray will be passing through optical center, light ray passing through the optical center, right? So this is the case. What we find here that the two light rays are intersecting at this point, so the image will be formed at this point. So this is the point where the image will be formed, right? And irrespective of the position of the object, whatever be the position of the object, we will always get the image like this only. And therefore, what we conclude from here is that for a concave lens, the image formed is always virtual, virtual is erect, right? And is erect and is diminished, right? And is diminished and is on the same side. Virtual image is always formed at the right. So the image formed here is virtual, is erect and is diminished and is on the same side. So this is the only image formation which we get for a concave lens, right? Irrespective of the position of the object, whatever be the position of the object on one side of the lens, the image formed will always be a diminished, virtual and erect image, right? So this is all we have for your image formation. Image formation. Now let's talk about the lens formula. The lens formula is 1 by f is equals to 1 by v minus 1 upon u, right? 1 by v on 1 by u. This is the lens formula. Again here we have to put the values using the sign convention, right? Next is your lens maker's formula. Now, what is lens maker's formula? Lens maker's formula is again derived using the formula which we saw for your for curved surface. What was that formula? That formula was your mu2 upon v minus mu1 upon u is equals to mu2 minus mu1 upon r, right? Using this for two different surfaces, that is for first surface and this is for second surface. So first for this surface and this for the second this surface, again we are not getting into the derivation, simply just I'm trying to tell you that in this case using this basic formula we get a lens maker's formula, and the lens maker's formula is given by your 1 by f 1 by f is equals to mu2 minus mu1 upon mu1 into 1 upon r1 minus 1 upon r2 into 1 upon r1 minus 1 upon r2, right? This is the lens maker's formula. Lens maker's formula, right? Now again, if this is a convex lens, this would be r1 and this would be your r2, right? So if we take r1 as positive, r2 is to be taken as negative. Now if we talk about a concave lens, for a concave lens this would be r1, so r1 will be negative and this would be r2, so r2 will be positive, right? So using the sign convention, putting the values, we will get the focal length using this lens maker's formula, right? And what is lens formula? Lens formula is 1 by f is equals to 1 by v plus 1 by u. Lens maker's formula is done. Refraction to the curved surface is done. Image formation is done. Now linear magnification, right? Linear magnification and power. So linear magnification here is given as m is equals to v by u, or it is equals to I upon o, right? The concept which I taught in the case of mirror is also true here. That is, very first thing is that if m is greater than 1, then the image form is magnified, right? M is less than 1, then the image form is diminished, right? M is equals to 1, then image formed is what? Image formed is of same size. What is if M is positive, then virtual image, and if M is negative, then real image. Let's see. If we see the ray diagram and we talk about real images, then for real images, V is positive, U is negative. Real images are inverted, so O is positive, then I is negative, right? So using the formula, M is equals to V upon U, so V is positive, U is negative, so we get negative. This is for V upon U, and if we use I upon O, I is negative, O is positive, so again we get negative. So for case of real image, we get magnification as negative. If we talk about virtual image again referring to the ray diagram, virtual image distance is negative and object distance is also negative, object height is positive, and image height is also positive. So we can clearly see from here that using the formula m is equals to v upon u, we get as positive, and using the formula m is equals to I upon o, we get m is equals to positive again. So for real images, the magnification is negative, and for virtual image, the magnification is positive, right? Magnification can also be given using the formula, that is your, yes, that is m is equals to m is equals to f upon f plus u, and is equals to f minus v upon f, right? These are also the two formulae which you can use for your numericals. These are, again, the sign convention, putting the sign convention is important, right? So this is your magnification, linear magnification, lens maker's formula, lens formula. Let me see what is left. Yes, power of lens. Power of lens is again is equals to 1 upon focal length. This power will be given in diopter if this focal length is given in meter, right? So this focal power is equals to 1 upon focal length, and if focal length is in meter, the power will be given in diopter, right? Then comes your combination of lenses. If two or more lenses are combined together, suppose this is a convex lens and is being combined with another convex lens, focal length of this convex lens is f1 and for this is f2, then the resultant focal length f will be equals to given by 1 by f is equals to 1 by f1 plus 1 by f2, right? Again, the sign convention is important. This formula is valid for all kind of combination, that is convex concave, convex convex, convex and concave concave, right? All type of formula. as all type of combination is this is valid. Now, if there is a separation between the two lenses, suppose this is one of the lens of focal length f1 and this is the another lens of focal length f2 and the distance between them is d, then the formula is being given as 1 by f is equals to 1 by f1 plus 1 by f2 minus d upon f1 f2, right? Minus d upon f1 f2. Again, sign convention is important. So if there is a separation between two combined lenses, whether it is convex convex or concave concave or concave convex, putting the sign convention and using the formula, that is 1 by f is equals to 1 by f1 plus 1 by f2 minus d upon f1 f2 will give you what? The combined focal length of the combination, right? Combination with mirror is not there, then coming to your optical instrument, right? So let's begin with optical instruments, right? So in optical instruments, the very first thing which we are going to study is the simple microscope. Simple microscope is nothing but your magnifying glass, and we've already seen the ray diagram for the magnifying glass. Let me see here. This is same as the ray diagram for the magnifying glass, the simply or the simple microscope, and this is how the micro objects can be seen with the enlarged image using the convex lens. And the convex lens is placed in such a manner that the object will lie between the focus and the optical center of the lens, and hence you will get a magnified virtual image, and hence the convex lens will be working as a simple microscope for us, right? Now coming to the compound microscope. Now compound microscope, no, not compound microscope. The thing which you have to know is the magnifying power. Magnifying power of simple microscope. So if we talk about simple microscope, uh, simple microscope, microscope, the magnifying power. Now, before talking about magnifying power, let me tell you there are two conditions at which the magnifying power is being calculated. The first condition is for normal eye or normal vision, right? And another case is for relaxed eye or relaxed vision, right? Now, what is the case for normal vision? Normal vision is the vision for the case when the image is formed at a distance of distinct vision, and distance of distinct vision is represented by capital T, and for normal uh, eye it is equals to 25 centimeter, right? It is equals to 25 centimeter. Whereas for the case of relaxed vision, the object is supposed to be formed at infinity, right? Object is supposed to be formed at infinity. So when the images are formed at infinity, we say that the instrument is used for relaxed vision, or it is relaxed eye and used with relaxed eye. And when the final image is formed at a distinct vision, distance of distinct vision, that is your, which is also known as near point, and the distance is of 25 centimeter, then that is known as normal vision, or seen with the normal eye. So for the case of, for in the case of a simple microscope, the magnifying power, when it is the case of normal vision, then the magnifying power is equals to m is equals to 1 plus d upon f. Here d is again your distance of distinct vision, and f is the focal length of the lens. Whereas for the case of relaxed eye, this formula becomes m is equals to d upon f, right? M is equals to d upon f. Next, coming to compound microscope. Compound microscope. Compound microscope. Now, in compound microscope, there are two lenses, right? One lens is your One length is known as eyepiece and the second length is known as objective. Then focal length of eyepiece we write it as FE and focal length of objective we write as FO. So FE is greater than FO, right? FE is greater than FO. Focal length of eyepiece is greater than focal length of objective, right? Now, what is the ray diagram here is? Let's try to understand. To me, right now, this is eyepiece. This is your eyepiece, and this is your objective, right? Now, the object is kept in front of the eyepiece, right? The object is kept in front of the eyepiece and the object is adjusted. The object distance is adjusted in such a manner that the image formed, and suppose this is the focus, right? This is the focus of eyepiece, right? Here it is the object. Now the object position is adjusted such that the image is formed as a real and inverted image. Suppose the real and inverted image is formed at this point, right? So the arrangement is adjusted in such a manner that the image formed because of the eyepiece. This is the image formed because of eyepiece, right? Falls between the focus and the optical center of the optical center of what? Optical center of objective lens, right? Now because now this image is falling between the focus of objective and optical center of objective. This image will work as a virtual object. It will behave as virtual object for objective, and then this objective will form the image for this object, virtual object. And when the object lies between focus and optical center, the image formed is virtual, erect, and magnified. So the image formed will be somewhere here because this is erect with respect to this magnified. It will act similarly as the what? As the magnifying glass. So this is how you get a magnified image in a compound microscope. I repeat, the object distance for eyepiece is adjusted in such a way that the real image formed by the eyepiece falls at a point which lies between the focus and optical center of objective, right? This is the reason why we take the focal length of objective large, so that the real image formed by eyepiece easily falls between the objective focal length and optical center of the objective, right? So when the image formed by eyepiece falls between focus and optical center of objective, the objective forms a virtual, erect, and enlarged image of the image which was formed by the eyepiece. That is, we get an virtual and enlarged image of the object, right? Now, the distance between the two lenses is known as the length of the microscope. The distance between the two lenses is known as the length of the microscope. Now, what is the length of the microscope? If you see, this length of the microscope can be divided into two parts. First part is this, and second part is this. First part is your image distance for eyepiece. Second part is your object distance for objective. So length of the microscope can be written as magnitude of VE plus magnitude of UO. That is magnitude of image distance. That is, we do not have to take the sign convention. Magnitude of image distance for eyepiece plus magnitude of object distance for objective. This gives you the length of the microscope, right? So, for a compound microscope, I repeat, object is so adjusted that the image found by the eyepiece falls between the focus and optical center of the objective, and when this image falls between the focus and optical center of the objective, it acts as a virtual object, and the image formed for this case is a virtual inverted and magnified image, and therefore we get a magnified image for this. Now this compound microscope can also be used in two modes, that is for a normal eyes and for a relaxed eye. So for normal eye, the magnifying power is given as your VO upon UO into 1 plus D upon FE, right? And for relaxed eye, magnifying power is given as length of the microscope upon FO into D upon FE, right? F L upon FO into D upon FE. D upon Fe. So this is for your relaxed eye, and this is what is for your compound microscope. Now coming to, yeah, this can also be written as, this is also equals to, this is also equals to VO upon UO into D upon Fe, right? Now coming to your telescope. Now what is telescope? Telescope is again used to see the terrestrial bodies, or the bodies which are in the space. So for terrestrial bodies we use a telescope, and what is a telescope? You can say the microscope is been reversed. It means in telescope again we have two lenses, objective and eyepiece. Here the focal length of objective is much greater than the focal length of eyepiece, right? Focal length of eyepiece. Again in this, what happens is the arrangement is somewhat like this. Suppose this is the objective and this is the eyepiece, right? And let this be the principal axis, right? So now the light rays are coming from infinity, right? Because the object is placed in space, so we can consider that object be placed at infinity. Now because the object is placed at infinity, the image will be formed at focal plane. The image will be formed at focal plane, right? So this is focus of objective So here is the image formed. Here is the image formed, and this is a real image. Now we need to see this. So the eyepiece should be so adjusted that the focal length of eyepiece is beyond the image formed by the objective, right? So if this is the eyepiece, then the image formed by objective should fall between the focus of eyepiece and the objective of the eyepiece. And when this happens, what will happen? The image of this image formed by the objective will be formed as a virtual virtual erect image as in the magnifying glass. So this is the thing. Again, here the length of the microscope is the distance between the two lenses. So again, the distance between the two lenses can be divided as your this distance will be this distance will be VO, and this distance will be this distance will be VO, and this will be UE, right? So again, here also the length of the telescope is given as mod of VO plus mod of UE. This will give you the length of telescope, right? And if you talk about the magnifying power, again this telescope is used in two cases, that is for a relaxed eye and for a normal eye. Then that is now for a normal eye, the magnifying power is given as minus FO upon FE into 1 plus Fe upon D, right? This is for your normal vision, for normal eye. Again, FO is focal length of objective, Fe is the focal length of eyepiece, and D is the distance of distinct vision. And magnification is also given as minus FO upon Fe, and this is for the case of relaxed eye. Relaxed eye means when the final image is formed at infinity, right? When the final image is formed at infinity. Right, so this is all for the optical instrument which you have to study for your NEET examination. And I would like to also tell you that the charges for your courses in MEMONEET are at the discounted rate right now. You can just go and avail it, and may avail the offer and enjoy the discount. So this was the things about ray optics. At this point, we end up with almost all the topics of the ray optics, which would come in the NEET examinations. If I missed any of the topic, or if any of the topic which is not understood by you in this videos or in diagram, or any other problem, please put it in the comment box, and I will try to resolve all the problems and make video on the on your problems, and whatever has been left out by me, or if you do not understand it, please put your comments in the comment box. And that is all from my side. Have a good day, and study well, study hard, and prepare well for your NEET examination. Please go to the MEMONEET app and avail the discount for the discounted courses going on, discount going on right now. Okay, have a nice day.